youth webinar. And today, Let Us Talk It is a platform where we build a informed and empowered community. Today, we have taken futuristic materials as our topic. And Vish is the moderator, so you can begin.
So what we'll be covering is, first of all, we haven't exactly gotten this, but first introduction, then materials, and then finally the Q&A. So, like Vivan said, my name's Vish and I'm the moderator for this week's webinar, and the topic is futuristic materials. I'll be talking about a material that can shapeshift and turn into liquid.
So thank you, Vish. I'm Vivan, and I'm going to be talking about one see-through material that we all know as glass, but it's not normal glass. And when you reach my slides, you'll know what I mean.
Hello everyone, my name is Zara, and I'm a sixth grader from Georgetown Easton Middle School. And for my material that I chose is going to be a particularly strong and conductive material. It can also be altered with alloys to change its structure. Like any other material, I'll show you at my slides.
So our materials now. We'll be going on to the materials that we've chosen. So the material I've chosen for the topic futuristic materials is liquid/shape-shifting metal, a metal that can change shape, move, and be programmed. The abilities of liquid metal/shape-shifting metal are, like I said, can be programmed to do things. Heat. When it gets hot, liquid metal can open up and shift, like breathing, shrink and enlarge. It can be turned into a sort of tiny ball and sort of blow up. Can be turned into a tiny ball and sort of blow up and enlarge. The uses and possibilities are it can be used for robots, buildings, and safe batteries. Possibilities can be used to make shape-shifting robots, nanotech with reform that can reform and reshape cars to be safer. How was it made? What just happened? Just a minute, I'll get that back. Something just happened.
Quick question, Vish. You didn't name the material. What's it called?
I already said. Did I?
No, you didn't mention.
Is your screen share not working?
Yeah, just lagged out. I'll get it back on.
In the meantime, I'll share. So do you see it?
Nope.
Okay. Just waiting for it to load.
Should I share again? Or do you want to take over?
Yeah, it's fine.
It's fine. So you're on this slide, right? Or no, you're on this slide.
Yeah. So how was it made? The way it was made was half a decade ago, a scientist, an engineer, and a businessman met in a Dublin backyard to conduct an experiment. They heated water in an electric tea maker and poured it into a bisected segment of a pipe. At the bottom of half pipe lay a length of wire, and one of the men held a ruler next to it. As the hot water gushed through the pipe, the wire shortened by several centimeters. When they poured cold water over it, it returned to its original length. The trio thought they might be onto something big. Some power plants and industrial users send their hot wastewater through secondary engines, which convert a small percentage of energy in that water into electricity using a process called called the organic Rankine cycle. This technology, however, requires chemicals to generate power from the heated water. Some of the best chemicals for doing this are dangerous or harmful to the environment, and therefore often banned or restricted. Cleaner chemicals do not draw enough energy from the waste or water efficiently. This adds to the operational costs of running these engines, which means they are not always cost effective, according to Jonathan Comey, an Earth System lecturer at Stanford University School of Energy and Environment Science, who is not associated with exergen. This is where the morphing wires come in. Shape memory allows alloys have unique molecular properties. They shift between pre predetermined shapes depending on their temperature. That is why this material is the heart of Exergen's new machine. It uses nitinol, a variation on original shape memory alloy. The name represents the fact that it is an alloy of a nickel, Ni, and titanium.
Wish,
Yeah,
is this a real material?
yes, it's real.
Oh,
I meant to, there was a slide about that, but I don't know what happened to it. And NOL refers to the Naval Ordnance Laboratory where nitinol was invented, says Preston McDougall, professor of the chemistry at Middle Tennessee State University, who is not connected to Exergen. At the molecular scale, nitinol is oddly orderly. Most alloys have no real structures at the molecular level. They are like solutions of metal as opposed to the order arrangement inside, something like a salt crystal or a diamond, McDougall says. Nitinol molecules, however, form regular cuboids with 90 degrees angles. Under a microscope, McDougall says, it looks like a bunch of stacked shoeboxes. Heat those molecules and they reorient themselves ever so slightly at the right angle become acute or obtuse, such as that the material contracts, cool the material, and the molecules regain their right angles, and the shape memory alloy returns to its original shape and size. Exergen's engine exploits this shape-shifting behavior to turn waste heat water into electricity. Its developers say the engine could be installed in a waste heat plumbing system where it could cycle hot water into its cylindrical piston chambers. Each piston is attached to a nitinol wire. As the hot water comes in, the wire contracts a relatively small amount but does so very powerfully, says Alan Healy, Exogen's CEO. Then the engine cycles cold water into the piston chamber. The nitinol expands and the piston springs out again. On the other side of the piston is a viscous liquid. The moving piston pushes the fluid through a hydraulic transmission that spins a generator, creating electricity. Using the properties of these materials to generate energy sounds counterintuitive, but it's not unique. advinculus. After all, scientists invented shape memory alloys over half a century ago, and engineers have long recognized these materials had energy harvesting potential. In 1970s, a mechanical engineer named Ridgway Banks, working at Lawrence Berkeley National Laboratory, developed a shape memory alloy engine that believed that could save power industry and other sector billions in energy costs. Banks to the engine, but it never revolutionized the energy sector as he hoped. Its technology was complex and required too many chemicals, and morphing wires wore out too quickly to be practical. But academics and engineers kept the idea alive in journals and laboratories around the world. In 2010, General Motors partnered with the U.S. Department of Energy and Advanced Research Projects Agency Energy to invite an array of waste heat recovery technologies, including some based on shape memory alloys. So far, however, GM has only used shape memory alloys to replace more complicated mechanical errata on its vehicles, such as device that makes it easier to close a Corvette trunk.
Wish.
Yeah.
Um, what you're saying is not relating much to your material. So,
It is good.
so you can move on to the next slide.
Yeah. Next one. No, there is. Except for the video. You can go to the next one.
Oh, do you want to move on to the next slide or?
There's one more.
Oh, this one?
Yeah, it's a video. It's about gallium, another shape-shifting kind of metal. You can go there. The video. Click on the blob. It's okay. It's not very long. You can put on full screen.
It is kind of long. It's like 9 minutes. Where do I stop?
You can stop like at 7. Should I present it? I think it's better if I present. You can stop sharing.
What?
You can stop sharing, I said. I'll just present it.
Oceanside Verbo is about to become the backdrop for an unforgettable vacation memory.
It's fine, Wish. We don't need to share the video. We saw the point.
Next, so fun video. We'll play to that. There we go.
If you take it out, you can see it's actually turned liquid. I'm tipping this out straight onto my hand, which I've read is safe to do so, but if you try this, you may want to consider wearing gloves. And you can see this core from the center of the test tube, which didn't have time to melt yet. It feels a little weird, and it sort of globs together in the palm of your hand. I decided to pour this out onto a plate to let it cool and see what it looks like. You can see as it's cooling, it starts to form these sort of crystal lumps too. It also stuck to my hand a bit, which you can easily just scrape back together. It has left this grey discolouring on my hand, which doesn't seem to wipe off easily. But if you use some soap and warm water, it cleans off okay. I'm putting this core straight into the bowl of warm water to melt it down. After a couple of minutes, it looks mopped via the key. So I took a lump of plasticine and this key from a padlock, which I pushed in to make a rough mould. I was keeping the gallium warm in a bowl of water, so I sucked it up and squirted it into the mould. You can see it doesn't really flow into the corners of the mould because the surface tension is quite high, so I don't think it'll work very well, but we'll see what happens. I'm also squirting some onto this paper plate to cool and spreading it out a bit. And the rest of it I'm just squirting into this bowl of water, which I'm leaving to cool down. I left it all at room temperature for a few hours to let it solidify. If we have a look at the paper plate, you can see if I bend the plate, it peels off quite easily. And we've got this really cool solid shape of metal. Where it's thick, it's really quite hard and difficult to bend. And in the middle, where it's thin, I can twist it and break it pretty easily. If we take a look at the key I cast, you can see it has got some of the features, but it is pretty rough. It's quite cool, but you obviously wouldn't be able to use it. It didn't really get any definition of the teeth. And the pieces we left to cool in the water did come out pretty well. Some nice shiny surfaces and interesting shapes.
Okay, now over here we are to Virat's presentation. Or is this just begun?
You got it wrong. It's actually Vivon, but yeah.
Okay.
Thank you, Vish.
Here we are at Vivan's presentation.
So thank you, Vish. It was a wonderful presentation about the liquid metal. But I have something to say about my material too. It's glass 2.0. So let's start with the basics. It has some strength and it's see-through. It also has flexibility. It's not brittle, meaning that it will break, and it's light and advanced. So these are some advanced details about it. It is electro and photographical and voltaic density. I'll talk about what this actually means in a little bit. So, Vish, next slide. So it is electro-optic, meaning that it can produce electricity using light, and it can produce light with electricity. So it does both things. So we all know that light bulbs can use electricity to make light. That is what it can do. Basically, it's a light bulb. And it can also be used as a solar panel. But I didn't intend it to be a solar panel, but still. Electro-optic meaning that it produces electricity using electricity, and photovoltaic means that it turns light into electricity. And this actually makes it glow even more because because it's using electricity to turn it into light. And some of the light that it gives off is turned into electricity, which is turned back into light, meaning that it glows a lot more and it's more efficient than a light bulb. So a glass 2.0 in theory could be used for electrical light bulbs. not just halogen light bulbs or other heat lamps or other things like that. So, next slide. Oh, go back slide. So, its properties. It can actually be used for magnetic properties because it's attained by the conductivity. It is very conductive, and we know that electricity produces magnetic fields. And further, it also has current density, meaning that its density and shape is changed by currents sent through it. And currents include electricity and other sources of electrons. And it's also made from normal materials found in glass. It's also electrochromic. Electrochromic means that it can change its color and how much light it lets through using electricity. This is very similar to sage glass. Sage glass is already an existing material that can that can let different parts of the spectrum go through, and it can be used as like a reflective or all kinds of other cool filters on glass. So I also forgot to mention on the last slide, it can be used as holograms. Uh, well, it can be used as a holographic because since it can give off light, it can since it can give off light and it's made of glass, it'll give that holography slash TV slash laptop look that you normally find in those movies, which would also be pretty cool. Next slide. So what is it made of? It's made of gallium arsenide, electrorestrictive graft elastomers, glass, and indium tin oxide. So why gallium arsenide? Well, this is one of the photovoltaic materials. It can produce electricity using um, light. It's basically one of those materials made for solar panels.
Or like
Electro-
the video, right?
Electrorestrictive graft elastomers are actually elastic materials that can change using electricity. Basically, how I talked about that it can bend. It's very flexible. And glass. We all know that glass is very brittle and it breaks. And this goes against what I said about it being not brittle. And but glass is see-through, so it adds. But what I mean that by that is if you make very thin glass, then it doesn't become brittle, it becomes flexible, which is a very interesting property of glass. And indium tin oxide. Indium tin oxide is mainly used for OLEDs, AMOLEDs, and LEDs used in computers, meaning that this can be used as a holographic part. This this is the one that turns electricity into light, and that's what it's made of. Next slide. So what are the applications? Well, you can make artificial muscles with this. Because, like I said, the electrorestrictive graft uh, elastomers are are little um, materials that can change shape and density based off of electrical currents and magnetic. Like I talked, oh, go back a slide. So, like I talked about before, it it gains electricity. Well, it begins it. Well, it is magnetic because electrical fields induce magnetic fields. And architecture. It can be used for normal glass purposes and more. And it can also be used for natural buildings. Like you can make it as if the morning, like as if night is morning, because since it can give off light and almost make it seem as if natural light is shining through the window when it's literally night outside, it can make you tricked into thinking that it's morning. And this could also be used on playing mean pranks, like making someone work through the night and everyone else is screaming at them because they are working through the night and they don't actually know um, that it's morning or night. And it can also be used for electrical purposes. Like I said, it can conduct electricity. But we all know the cables and fiber. Yeah, fiber. Fiber sends um, electrical signals using the um, light signals. We all know that light is very, very fast, and it can travel across the Earth in probably a few seconds. Meaning that if you use this glass, it can also turn up the it can um, amplify the signal, or it can even change the signal because it can produce light or it can absorb light. So it can be used for other similar purposes, including cable and etc. They can be used for a lot more. And there are quite a few things I didn't think about, but it may be used for, like solar panels. Solar panels are something I haven't mentioned here, but they are something I mentioned in a previous slide. Since these can turn um, like photons into electricity, it can be used for that purpose. That is all about Glass 2.0. Thank you.
I find it interesting, Vivan, that how much in common gallium and glass 2.0 have together, right? I mean, like, both of them change shape, and gallium's even one of the materials, right?
No, not exactly. Gallium arsenide is a different material. Arsenic makes it very different from its actual gallium state. So I'm actually done. You can move on to that slide.
With all these properties, would it make it a metamaterial? Would it give possibilities for invisibility?
Your voice is kind of cracking up.
Um, so with all these properties, could it be a metamaterial? Could it give possibility to invisibility?
Maybe. Yeah. I think that's a definite thing that may be coming. Invisibility cloaks. I could just imagine that.
And
So
it's cool how it can replicate the light
yeah.
and
So
make holograms.
move on. You can move
Hey,
on to Virat's slide.
yeah. You could morph. You could see through objects, and you could make holes.
Virat,
Now,
Virat, it's your turn.
yeah, I know. You could morph materials. You could see through materials. You could make holograms, and a lot more. But what if it comes to strength? Well, then graphenite has your back. This is obviously not a realistic material because it's 300,000 times stronger than graphite, but it could be a possibility in the later future. Anyway, graphite is 300,000 times stronger than graphite, like I said, or to put it in a sense of scale that you might understand, but still not understand. Next slide. 60 million times stronger than steel. Yes, 60 million times stronger than steel. That is insanely strong. Not even a bullet
Um,
or a
Virat, your voice is like very, very off, and something keeps getting in the camera. I think it's your finger.
What about now?
Yeah, it's great.
Okay. So 60 million times stronger than steel, that is ridiculously strong. And to put it to a strong sense of scale, is that a bullet wouldn't even stand a chance, and a bomb would do nothing. I'm not saying that graphite can't be altered or defeated. I'm just saying that it's really strong, but it has some disadvantages and it's not indestructible as it may seem. It can actually be destroyed. But depending on how you alloy it, it can actually become indestructible. But then again, that would cause a lot of problems. Next slide. It's shapeable and reformable, and that brings it down to like just because it's super strong doesn't mean that you can make robots that take over the world and no one can do anything to stop them. If you apply just enough heat and then you cool it down really quickly, then it will shatter. Or if you just heat it up, then it'll start bending as if nothing happened. So these are the materials that it is made of. These are alloys. 3 of these materials aren't real materials. But anyway, Tita, which is basically a light version of titanium, it's as strong as titanium, but it's actually lighter. Titanium gives it the strength, and the Tita part of it makes it a lot lighter. Copper, gold, and copper, the most conductive materials on Earth. I know gold might seem overkill, but no, seriously. Every device that you have, every electronic device is 1 to 2% gold. So it wouldn't be unreasonable to mix them together to get a very conductive one, gold, and a really durable one, copper. And also, copper is a lot easier to deal with. Then we have silicon. Silicon is an insulator, meaning it doesn't transmit heat or energy really quickly, and it more likely dissipates it. So it's a really good one, and that allows it to have some properties like that make your electronics a lot smaller. If we didn't have silicon, then all our electronics would be sending sparks everywhere and there would be errors and there would be constant malfunctions. We don't want this. Silicon makes sure that no electric sparks can cross across a microchip or a motherboard. So, depending on how much percent silicon you add, it can make it more durable or more insulation. And finally, we have adamantine. The adamantine isn't actually very special and it has nothing to do with the real world, but it was in Greek mythology. It was known to be impenetrable. And that's why the gates of Tartarus are made of it, because it's impenetrable. The gates of Tartarus are basically the gates from life and death. But the adamantine that I'm talking about is not indestructible. It actually has a specific strength. So let's just say it's really strong. Depending on how much adamantine is added, that changes how strong it is in general. So 60 million will increase the amount of adamantine to 50%, and you have a 120 million times stronger than steel. Next slide. Ideas and reflections on this material. Well, the concepts to these materials involve better computers. You will get better computers because, like I told you, depending on the silicon, it can become a better insulator, and that also means that we can go smaller and smaller with our technologies. And depending on how much gulper you put, it can also increase its, conductivity. Basically meaning that if you made a computer with zero insulation and a lot of insulation, then you can have a computer pretty much made of this material. It's also really easily able to be mass produced because it is easy to find. Well, kind of on the arbitrary scale. I mean, it would only be easy if you were to go into the mantle. We barely scratched the crust. But once we destroy the crust, dig a hole through the crust to the mantle, all these materials will be able to be found. Tita, which is basically titanium, this will be found a little bit into the crust, but mostly into the mantle. Gold and copper, or gulper, it can be either an alloy or found naturally in the mantle. Adamantine, found inside the mantle, really rare in the crust. And finally, silicon. There are a lot of high silicon rocks and silicon in the actual crust. So you won't find that much in the mantle, but still, 2% of the whole entire mantle is just silicon. I mean, just because I say the mantle don't get discouraged that there's not much of this material, or it's actually not that easy to get. The mantle is thousands of times bigger than the crust. So now where and how? It is really conductive, like I mentioned about copper, and it can also be used for nanotechnology. So it can reform and reshape. Since it can reform and reshape, it can move around in specific ways. And like Wish said with his material, it can practically be programmed to go somewhere. And it's also affordable. Like I said, even though it's hard to find at first, we will be able to get to it in the mantle. And once we get to the mantle and we get some of this material, there's nothing stopping us. We're basically going to be indestructible. We can just create more machines that are capable of going into the mantle, and then we get more of that material, more machines, more material. And don't get discouraged to Earth also, because there are a lot more planets just like Earth that may have these chemicals too, or minerals. It's also very easy to process because of its very light chemical composition. It doesn't have a lot of special chemical bonds, and it doesn't have any complex polymers. It's just a simple material. So, next slide. The applications of this material. Well, it can be used for better computers. I explained. It can be used for building, as I said, 60 million times stronger than steel. Your concrete is reinforced by steel. Now, what does this mean? Well, buildings are 60 million times stronger. Yes, that may seem a little insane at first, but yes, your buildings are going to become indestructible. And we have automobiles. Previously, we had cars and things like that had exoskeletons. This took up a lot of space in the car, and it also reduced the efficiency and how fast and how much of this mobile that we could create at once. Even though it was being mass produced, still, we can make things a lot better for automobiles with this material because it's conductive, allowing us to make the electronics in it. It is also really strong and durable, meaning no fancy exoskeletons that may take up a lot of space in the car, allowing more things. And that was pretty much all for automobiles. Next, we have rocket and airplane. The rockets and the airplanes, basically, they go into the outer atmosphere or outer space, and there are really harsh conditions here, especially for an airplane. If it was heading toward the ground at incredible speeds and it crashed into the ground, then it might cause a lot of impact and kill a lot of people. But no, we can create graphite seatbelts. They're indestructible seatbelts that absorb a lot of force. And this material, if engineered in a specific way, could absorb a lot of shock, also helping automobiles that a lot of the shock from a sudden crash because of the conservation of momentum and inertia, well, no need to get worried about that because it's all reduced. Then we have water vessels. Since the depths of the ocean, just few hundred feet, could cause a lot of pressure, like a ton of pressure trying to push and crush that material. Well, no, we don't have to do that anymore. Since this material is practically indestructible, the pressure is no more gonna do anything. And then we have power. Since it is really conductive, it can be used to make batteries a lot faster. Not just batteries, but it can also make some other parts of a computer faster, like some of the computer parts like a CPU or a GPU, or even make it smaller to pack even more of that. And then deployment. I mean, it could just easily, you could take that material, make a machine to make that material that uses that material to make more of that machine that makes that material, and goes on until you make lots and lots of graphenite. And then manufacturing. You can manufacture a lot of things, and it takes a lot of effort. Well, there can be things that go wrong in the manufacturing process. To stop anything from going wrong, you need power and something that's strong. So graphite will do. I mean, it's also for the conductivity and other things. Hydraulics and force. Since it's really conductive, it can be used to make better motors. Better motors meaning better hydraulics. And that allows for really strong pistons. It also helps airplanes, rockets, and automobiles. So that was pretty much all for my material. That was a lot to pack in, but yeah, that's pretty much the whole entire of the material.
And now, that's all we have for this week's webinar on futuristic materials. So here we are, moving on to the Q&A.
Yeah. Okay, you can unshare now, Vish.
Okay. What are some questions you guys have?
Okay, so out of all of them, what would we call the lightest material?
Well, I mean, like, not clearly explained that. The
Okay.
glass. What's the glass called?
I yeah, it's Glass 2.0. I guess it would be useful for a lot of like diverse applications, but in Varob's case, he seems to explain its like strength, which is also a diverse thing, but it can only help so much. Strength isn't what we necessarily need. Like in some situations, you don't need a strong material; you need an effective material. Like for computers, you don't need
True.
for computers you don't need a strong cooling system. You need an efficient one. You don't need strong batteries, you need efficient batteries. Same same goes for a lot of other things. Especially
Yeah, but with the help of this material and specific alloys and variations of this material, you can make efficient and strong and durable. All of these combined.
Well, where's this going when we're talking about the lightest?
it depends on like what we want to use it for. But in general, either one could be useful. But Morphite, on the other hand, it's basically just a smaller version of some already very good materials that are out there. If Morphite was eventually discovered to do more things, especially in like medical and technology, then it would.
But anyway, yeah, what's the lightest material though?
Probably more funny for like my material. I mean, like, it can turn into liquid, and liquid is really light, right?
No. Water, just itself, a cubic meter is over a ton.
Okay.
So Your liquid form may be a little heavy.
but it's way more transportable.
I mean, since when it becomes a solid, depending on its density, since it can change density, it's more fine, of course. Depending on its density, size, and some other relative measures, it could be heavier or lighter.
But I think my material is very, very light. In comparison, I actually researched on these materials that it's made of. Like gallium arsenide, like Vish said, gallium and morphite was the material. They are actually very light. And the other materials like glass isn't that heavy. And since my material is flexible and you can change its density, you can make it so it's very, very dense, so you can easily carry it around, and you can bend it into multiple sheets where you just need to extend it into whatever you want it to.
Okay, so we're done with what is the lightest. Then what would be used for what is the easiest to get, or what would be the fastest to develop?
Well,
Now that I'm thinking about it, that would be two separate questions.
Vic would
mine
Vic
probably.
is probably the easiest because because it is already out there. All you need to do is just make some modifications and put it to use.
Yeah.
But
Which
still,
durable then?
Hmm?
Which one would be the most durable?
of course, it's graphite.
Wait, no.
Now yours can.
Durable as in long lasting or strong? Because there are a few materials that are long lasting but they aren't strong.
Okay.
Which one? Which?
That really depends.
Long lasting or strong?
Well, gallium probably wouldn't be the most long lasting since it loses its properties after quite a while.
I mean, in gallium and morphite in their liquid form, they could easily be evaporated and put into the air, so that wouldn't last very long.
Yeah. But I mean, glass could break, but Vivan said that his glass is super strong.
I didn't say it was super strong. I said
Also,
it was flexible. And when something is flexible,
Um,
let's say you're trying to fight paper, you couldn't possibly rip like a paper by hitting it. You need to try something very hard on it to get it to break or something.
so Virat again.
it's true, but again, it's like one more thing about the modifications of Sage Glass. Sage Glass, well, I mean, Glass 2.0. The Glass 2.0 would have even though it's glass, it's flexible, and that disallows its
No, no,
ability to be tempered.
no. So actually, glass itself is flexible, not glass, but it's flexible.
No, I know, but what I'm saying is that it won't be able to be tempered. Tempered basically meaning it's strengthening glass, putting a plastic layer on top and on the bottom.
I don't think you need to. Do you?
No, it would be impact resistant and make it more than twice as strong.
I think that's how it will work. Yeah.
But again, like I said, because of its properties, tempering would be disallowed.
Um. Wait, but well, technically, you could just easily temper it by inducing a very, very high electric field, so it turns super dense. So it isn't like paper; it's like touching a solid brick wall with your finger, with let's say the Superman force. So your finger would break.
Uh-huh.
Okay, still, graphite wins.
Yeah, so graphite wins that argument?
What's the fastest to develop? Most opportunities, most
We just went over that.
we did?
Yeah.
What was it?
It was gallium because it's already out there, and we just need to make a few modifications,
Okay.
put it to use.
What would be like the best one?
Well, let's put a voting.
It wouldn't be effective voting. It's only 3 people. You could just easily vote for yourself and nothing would happen.
I guess. Anyway, which one you would think?
I'm choosing Glass 2.0.
Same thing.
You can't choose for yourself.
And now I just forgot what we're voting for. Ow. What are
You
we
can't-
voting for?
You vote for which material, not for yourself.
Which material would be the best?
Yeah, not for yourself though.
Yeah, I guess it would probably be Glass 2.0. Since like holograms are cooler than strength, right? Okay.
Oh, it's a tie.
And we're all tied again.
Wait, how more fight?
Huh?
Because it bends.
Yeah, we can't vote for ourselves. I would choose it, but we can't vote for ourselves. So
He doesn't need to. He can vote mine.
why don't we see what the spinner says is the coolest?
Okay.
That
You want
doesn't.
to do the spinner?
We can end it now.
I think we
Yeah.
should do the spinner before we end it.
Fine.
Yeah.
Hey,
So
what is the
So
coolest?
today was a very nice webinar. We went over some cool materials from the future. I'm thinking that may be developed, and a lot of cool ideas have been shared in this webinar. And shortly, we're going to be beginning our topic discussion. Anybody who wants to stay over, wait, no, you can stay over.
There is no one here.
What?
There is no one here.
Um,
Anyway,
Anybody could be watching from Facebook or YouTube, so technically they are here.
and the winner is
That seems reasonable. Okay. So we can end it off.
Aww.
We can end it off right here. So it was a great one, and just we can end our live session.
Okay. Bye.
Yep. Thank you. Oh, you're not leaving.
Yeah, I know.